Cosmic Forges, How Stars Create Every Element, and You. Hello, and welcome to Cosmic Enigma. Today we're diving into one of the most profound stories in the universe. Look around you, the screen you're watching this on, the air you breathe, even the very atoms that make up you. They all share an extraordinary cosmic origin story. It's a journey billions of years in the making, from the simplest ingredients to the rich tapestry of elements we see today. And the universe's ultimate alchemists. They're the stars themselves. This incredible process, known as stellar nucleosynthesis, reveals why, in a very profound and literal sense, all living beings are composed of stardust. This deep connection between the abstract processes of astrophysics and the tangible reality of human existence transforms a purely informational subject into an engaging story of cosmic heritage. Before the first stars even flickered, the universe had its own explosive birth of elements. Right after the Big Bang, in just a few chaotic minutes, specifically between approximately 100 and 300 seconds, temperatures and densities were so extreme that fundamental particles fused. This was Big Bang nucleosynthesis, forging the lightest elements: hydrogen, deuterium, helium-3, and helium-4. A tiny bit of lithium and beryllium also formed. But that was it. The universe expanded and cooled too fast for anything heavier to form. Think of it as a cosmic pressure cooker that quickly lost its heat, only allowing a few basic ingredients to form. This initial burst of element formation, while foundational, was inherently limited in its scope. The universe's initial chemical composition was thus largely confined to hydrogen and helium, setting the stage for subsequent, more complex element synthesis within stars. This limitation underscores that while the Big Bang was the genesis of matter, it was merely the beginning of the universe's chemical evolution. Hundreds of millions of years after the Big Bang, gravity took over. Vast clouds of hydrogen and helium collapsed, heating up until their cores ignited. The first stars were born. This ignition marked a truly transformative phase in the universe's chemical history, as stars emerged as the primary engines for creating new elements. The process through which new atomic nuclei are produced inside stars via nuclear fusion is precisely what is termed stellar nucleosynthesis. If Big Bang nucleosynthesis was the universe's initial ingredient dump, then stars are the cosmic kitchens where those simple ingredients are meticulously cooked, combined, and transformed into an astonishing array of new elements. The immense gravitational forces within a star's core are the critical enablers of fusion. Gravity creates the extreme heat and pressure necessary to overcome the natural electrical repulsion between positively charged atomic nuclei, allowing the powerful, strong nuclear force to bind them together. This delicate balance between gravity's inward pull and the outward pressure generated by fusion reactions maintains the star's stability throughout much of its life. The continuous interplay between gravity and fusion dictates the entire sequence of element creation within a star. Gravity acts not merely as a catalyst for star formation, but as the fundamental orchestrator of cosmic alchemy, driving the subsequent stages of element synthesis as a star evolves. For the vast majority of their existence, spanning billions of years for stars comparable to our Sun, stars reside in their main sequence phase. During this longest and most stable period, the primary energy-generating process in their cores involves the fusion of hydrogen into helium. This continuous nuclear reaction releases tremendous amounts of energy, providing the outward pressure that perfectly counteracts the star's immense inward gravitational pull, thus maintaining its equilibrium. The specific pathway for hydrogen fusion depends significantly on the star's mass and core temperature. In stars like our Sun, which are relatively smaller and cooler, the dominant process is the Proton-Proton PP chain. This multi-step reaction involves 4 individual hydrogen nuclei, essentially just protons, combining sequentially to form a single helium-4 nucleus, with the concomitant release of energy in the form of positrons, neutrinos, and gamma rays. This process can be visualized as tiny Lego bricks representing individual hydrogen protons meticulously clicking together to construct a slightly larger helium brick, with a small amount of energy dust escaping in the process. In contrast, more massive and hotter stars utilize a different and more efficient mechanism known as the carbon-nitrogen-oxygen CNO cycle. In this cycle, nuclei of carbon, nitrogen, and oxygen act as catalysts. They participate in a series of reactions that convert hydrogen into helium, but they are regenerated at the end of the cycle, meaning they are not consumed in the overall process. The CNO cycle is significantly more temperature-sensitive than the PP chain, making it the primary energy source in stars with core temperatures exceeding 15 million Kelvin. This fundamental difference in dominant fusion pathways based on stellar mass and temperature is a critical aspect of stellar evolution. A star's initial mass is not merely a descriptive characteristic. It is a fundamental determinant of its internal nuclear processes, influencing its structure, energy output, and ultimately, the types and quantities of elements it will produce throughout its lifespan. The CNO cycle, for instance, leads to a convective core in massive stars, which impacts how hydrogen is mixed and consumed. This understanding of mass dependency is essential for comprehending the vast diversity observed in stellar nucleosynthesis. As a star exhausts its primary hydrogen fuel in the core, the delicate balance between outward fusion pressure and inward gravitational pull is disrupted. Gravity begins to assert dominance, causing the stellar core to contract and heat up dramatically. This contraction and heating trigger the subsequent, more advanced stages of element creation. For stars of various masses, the next major stage is helium burning. If the core temperature reaches approximately 100 million Kelvin, helium nuclei, also known as alpha particles, can begin to fuse. The primary reaction here is the triple alpha process, where 3 helium nuclei combine to form one carbon nucleus. Carbon is a particularly crucial element, as its formation from helium represents a bottleneck in the entire process, laying the groundwork for the synthesis of even heavier elements. Beyond carbon, helium can continue to fuse with existing elements through the alpha process. For example, carbon can fuse with helium to form oxygen, and oxygen can fuse with helium to form neon. Only truly massive stars, those with masses roughly 8 times that of our Sun or more, possess the sufficient gravitational power to continue this cosmic alchemy beyond helium burning. As their core fuels deplete, these stars undergo further contraction, reaching progressively higher temperatures and densities. This leads to the ignition of new fusion stages in concentric layers, creating an internal structure often likened to an astronomical onion. These advanced burning stages include carbon burning, occurring at temperatures around 600 to 900 million Kelvin, which produces elements such as neon, sodium, and magnesium. As temperatures climb to approximately 1.5 billion Kelvin, neon burning results in the formation of oxygen and additional magnesium. At about 2 billion Kelvin, oxygen burning yields silicon and sulfur. Finally, silicon burning is the last stage of nuclear burning in massive stars, occurring at core temperatures of approximately 3 billion Kelvin. Through a complex network of reactions, silicon-28 undergoes photodisintegration, breaking into helium nuclei, which then recombine to form iron and nickel, known as iron peak elements. This remarkable chain of fusion reactions culminates in the formation of iron. The reason for this energetic endpoint lies in the fundamental nuclear physics of iron. It possesses the most stable atomic nucleus. While fusing lighter elements to form heavier ones releases energy, thus powering the star, fusing iron into anything heavier requires an input of energy. It does not produce it. This can be thought of as a factory assembly line where up until iron, each step in the production process yields a little extra power. However, at the iron stage, the line suddenly demands power from the factory itself to continue. The star simply cannot sustain itself anymore through fusion. This iron wall is not merely a chemical boundary. It represents a profound thermodynamic crisis for a massive star. When the core becomes dominated by iron, the star loses its primary internal energy source that has been counteracting the relentless force of gravity. This energetic constraint is the direct cause of the core's catastrophic collapse, which in turn sets the stage for a supernova explosion. This critical turning point in the cosmic narrative of element formation illustrates how the binding energy of atomic nuclei dictates the dramatic end-of-life events for massive stars, which are essential for creating elements beyond iron. Once the core of a massive star becomes dominated by iron, the star faces an insurmountable energetic crisis, as further fusion reactions cannot release energy. Without the outward pressure generated by energy production, the star's immense gravity triumphs catastrophically. The iron core collapses inward in mere milliseconds, then rebounds with an unimaginable shockwave, resulting in a spectacular event known as a supernova explosion. These supernovae are far more than just beautiful cosmic fireworks. They are absolutely crucial for the creation of elements heavier than iron. The extreme energy and intense neutron flux generated during a supernova provide the unique conditions necessary for processes like rapid neutron capture, also known as the R process, and proton capture, P process. In the R process, atomic nuclei rapidly absorb a large number of free neutrons, becoming incredibly heavy and highly unstable. These neutron-rich isotopes then undergo a series of beta decays, transforming into stable, heavy elements such as gold, uranium, and platinum. However, for the very heaviest elements, particularly the truly rare and precious ones like gold and platinum, recent astronomical discoveries have pointed to an even more spectacular and powerful event: the collision of two neutron stars. When two incredibly dense neutron stars, the remnants of massive stars, spiral inward and violently merge, they create an environment with an extreme neutron flux that far surpasses even that of a supernova. This fleeting but intensely neutron-rich environment serves as the perfect crucible for the R process, forging approximately half of all isotopes heavier than iron. If supernovae can be considered powerful factories for heavy elements, then neutron-star mergers are akin to a Mount Doom, the ultimate, most energetic forge in the universe, where the rarest and most precious cosmic treasures are created. These cataclysmic events, supernova and neutron star mergers, are not just endpoints in a star's life cycle. They are vital mechanisms for dispersing the newly forged elements into the interstellar medium. The powerful explosions scatter this enriched material, including elements from carbon to iron and beyond, throughout the cosmos. This enriched gas and dust then becomes the raw building blocks for subsequent generations of stars, planets, and indeed, for the complex chemistry that underpins life itself. The understanding of heavy element origins is not singular, but dual, involving both supernova and neutron star mergers. This refined understanding, driven by recent observations, adds significant depth and cutting-edge information to the narrative of cosmic element formation. The emphasis on neutron star mergers as a distinct and powerful source, especially for the rarest heavy elements, also provides a compelling explanation for why our own solar system is relatively rich in these precious metals, suggesting that our cosmic neighborhood may have been influenced by such a rare and powerful event. From the simplest hydrogen atoms born in the fiery crucible of the Big Bang to the carbon atoms that form the backbone of our DNA, meticulously cooked in the hearts of red giant stars, to the iron in our blood forged in the explosive deaths of massive stars, and even the gold adorning our fingers created in the violent collision of neutron stars. Every atom surrounding and composing us carries an extraordinary cosmic origin story. Stars are not merely distant points of light in the night sky. They are the universe's tireless alchemists, ceaselessly transforming matter and enriching the cosmos with the very elements necessary for complexity and life. Their grand life cycles, culminating in dramatic deaths, are the fundamental processes that make complex chemistry, and consequently, all known life, possible. The profound statement by Carl Sagan, "We are star stuff," is thus not just a poetic metaphor, but a scientific truth. Humanity is literally made of recycled cosmic material, forged in the fiery hearts of stars and dispersed across the universe over billions of years. This cosmic heritage underscores the interconnectedness of all things and offers a powerful perspective on our place within the grand narrative of the cosmos.